So, as promised, we're going to start talking more seriously about group actions. And group actions are one of the most important things that groups do, because the symmetry, you can find out things about sets, about groups themselves, by the way they act, and they're important in symmetries and all kinds of sciences and mathematics. We're going to start off on sets. So I'm going to go a little bit out of order with my notes, but I'll keep my notation the same so that you know where it's at. Let's suppose set. So this is us kind of calling this. We say G acts on A if there is this function G cross A into A such that one, the identity acting on A is A, so the identity leaves everything. And two, G1 acting on G2 acting on A, G1, G2 acting on A. Now, I'm going to start off. Now, what we're going to focus on here is that sometimes, really, a good set for a group to act on is the group itself. And I'll show you a place to do it. As 5. Symmetry. Oh. Great. There you go. I mean, this is actually one of the first ways that we kind of illustrated now group theory, right? So we think of D5 acting on this set of different arrangements of this pentagon. One way to do it, that's a 72-degree clockwise spin. That's flipping around the y-axis, right? And there's actually 10 of these things. So if you go through all the symmetries and multiply them out, you'll get the 10 elements of D5. You've seen that. And this is a good example of group action. You're acting on the rearrangements that way. And in a certain sense, you can think of that group as acting on itself. Example. Let G be group. G can act on itself by conjugation. So what I mean by that is, if G and X are in G, so I'm acting on the group itself, G acting on X is GX G inverse. This is a conjugation action. Somebody tell me why this action might not be too interesting if G is an abelian group. If G is an abelian group, then what's the outcome of this? It's just X. And so if G is an abelian group, this is a trivial action, right? It just everything's left alone. But if G is not abelian, this can be quite interesting. Conjugation, G could also act on itself by left multiplication. So if G X is in G, then G acting on X, just GX. Now, even though that might seem a little silly, this is also useful as well. Right? Notice this is an action because the identity acting on X gives you X. And the fact that the group multiplication is associative shows that the other, the G1, G2 acting on X, is G1 acting on G2 acting on X, right? Yes.
It's like if G is the subset that it's acting, like if G is acting on itself, is it correct to also just do like G times G times X equals G times G?
Oh, right. So yeah, I'll go through this. And two, tell me if this doesn't address your question. G1 acting on G2 acting on X. Well, by our definition, this is G1 acting on G2X. Because that's what the rule says.
Is that like associativity of groups?
That's exactly what it is. Right. And this is G1, G2X. But the associativity allows me to put parentheses around the G1, G2. Right? And by its very definition, this is G1, G2, circle X.
And then so what would that, like if that's called like conjugation and that's called
Left multiplication.
Oh, that's okay.
And actually, I'm going to give you a specific example of this one. This will illustrate some of these permutation actions that we'll have in a bit. So let me give you a specific example of this, and I'm going to do it actually with an abelian group. I'm going to come back to the older stuff. This is actually an example from a little further in the section. I'm going to let G be C6. Let G act on itself via addition. So I'm going to change the word multiplication to addition here because this is a abelian group. Let me point out, and I bring this up, and this sort of underscores, we're going to get to why this is important in a moment, but this is kind of a preview of this. This action gives a permutation set. So, you know, 0 plus X equals X for all X's, right? So the 0 bar acts on X by leaving everything alone. So 0 changes nothing. It leaves everything alone. It doesn't mean anything. However, what happens with 1 bar? Look at just the way 1 bar acts on the group. right? This is what one does to every element of the group, right? One's acting on these elements in the group. Right? This actually induces a permutation, doesn't it, right? This gives rise to the permutation, 0 goes to 1, 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes back to 2. Let's see. 1 pushes 0 to 1, it pushes 1 to 2, 2 to 3, and so on. So you can think of this as inducing permutation. What is 2 bar then? Well, two bars. 4 bar. You may think, well, this is not really, I mean, you're just shifting the whole thing down, aren't you? But something kind of interesting happens here. What's the permutation induced here? So the action of 2 bar added on the left here, where does it take 0 bar? It takes it to 2 bar. And then where does it take 2 bar? To 4 bar. And where does 4 bar go? 0. So you close off the cycle. So it's like a permutation. I haven't seen 1 bar yet. Where does 2 bar push 1 bar? Where it pushes it to 3 bar, pushes 3 bar to 5 bar, and 5 bar back 1 bar. So notice this is a 6 cycle. This is a product of 2 disjoint 3 cycles. Let's see if we can get this one writing it down. Where would, if I do 3 bar action, so 3 bar plus everything, where does that push 0 bar? 3 bar. And it pushes that. Right. Notice that for each one of these elements, Z6, 0 bar, 1 bar, 2 bar, and 3 bar, I guess we went through, it gives you a permutation of those 6 elements of the group. This is actually a rather important example that we're going to generalize in just a bit. Okay, let's start with the theorem here. Theorem 512. Let G be a group, A a non-empty set, and S a the set of permutations. And this is kind of in keeping with the notation that we've been using before. SA is the set of permutations. And this is, of course, synonymous with the permutations by this is just a set of bijections from the set of A to itself. A permutation is a one-to-one analytic function from a set A to itself. Then there is a bijection. So this is a big theorem. This is another one of these one-to-one correspondence theorems. There is a bijection between the actions of G on A from the actions of B on A to the set of homomorphisms from G to SA. Homomorphism. from G. SA. Remember, this group of bijections forms a group. And I'm gonna tell you how it's given. So this is actually amazing because what this says is, this is sort of like, do you remember when you had, when we talked about equivalence relations, and it turns out that if you have any equivalence relation, it gives you a partition of the set that it's on. And any partition of the set gives you an equivalence relations. So these things are essentially the same. That's what we're saying here. There's a one-to-one correspondence from any action that you can come up with, G on A, gives you a homomorphism from G into the permutations of SA. And vice versa. And actually, I gave you a small example of that with taking that action of left multiplication on Z6 to this collection of permutations to get rise to. And here's how, yes.
So it's specifically a bijection, not an isomorph. So you don't maintain.
Well, for there to be an isomorphism, you'd have to put a group structure on both of these. Right? And these are homomorphisms, and this is an action, so. So it's, yeah, it's bijection, it's one-to-one correspondence. Given by. So here's how it's given. G acting on A is equal to B of G of A. Where B and G SA is the homomorphism. So here's the way bijection works. If I walk up to you on the street, I say, here's my homomorphism from G to SA, and you're saying, okay, so the action is just take that homomorphism and apply it to A, and that gives you the A. And on the other hand, if I have this action, I can use this to get this homomorphism that's claimed. So let's go through the proof of this. Suppose first that B from G into SA is a given homomorphism. I'm going to demonstrate that as claimed, we get this action. We define so given this homomorphism, I claim that this is actually a group action. Now let's think about what this is. G acting on A should barf out something that's an A. That's what group action is. What is phi of G? Phi of G, this whole blob right here is just some function from A to A that's bijection. So when I input an A to it, I should get another A out. So at least I'm going where I'm supposed to go, right? The output of this thing should be something in A, because this is a function. This is a permutation of A, and this is an input of A. Everybody okay with that? Okay, well, let's look first. E acting on A is phi of E, but phi is a homomorphism from G into SA. So what happens when you plug in the identity of G into a homomorphism? What should you get? You should get the identity of SA. And this is the identity function. So you get A. Okay, so the identity does what it needs to do. How about that other business? Suppose G1, G2, suppose that G1, G2 acting on A. Well, by definition, this is phi G1, G2 applied to A. But again, this phi is a homomorphism. So this is phi G1, phi G2 applied to A. Now remember, this is being multiplied in the structure of SA. So this is a function composed of a function, right? Because these two elements are elements of SA, so they're bijection. So we're doing function composition here. So this is BG1, whatever that function is. BG2. Okay. So this looks to me like G1 acting on G2 acting on that, which is exactly what I want. Because G2 acting on A is this thing, and then you act on it by. So we have a group action.
Like the group action is that referring to is
Right. What we're doing here is we're starting with a given phi, and we're showing that this rule here that I just made up for fun actually is a bona fide group action. Okay. So what we have so far is if you give me phi, I can give you a group action by making that definition. All right. Now suppose that we are given an action, right? So the first thing I did was I was given a homomorphism, I made an action. Now suppose I'm given an action. So now suppose given some G cross A to A. So I want to come up with this homomorphism here. I am going to find so I need a homomorphism from G into SA. How am I going to do that? I'm going to define this homomorphism by E. Okay. Input G, I need some logical output that is actually a permutation of G. So let me cheat a little bit. Say pi G, where exists where pi G is permutation of A reduced by action. So when you say that this is a permutation, so pi G of A, what do you suppose it should be? So, okay, there you go. That's how we use the action. Pi G of A, this permutation is just whatever G does to this under the action that we're given. Everybody okay with that? Okay. By the way, can somebody explain why this is 1-to-1 and all two? I mean, this thing right here, it's not a homomorphism because it's just a map on a set, but it should be a bijection.
You repeat that?
So my question is, this pi g here, this is a permutation of A. So in particular, the function itself should be 1-to-1 onto. Right, so
But aren't we doing, isn't phi supposed to be a homomorphism?
what's that?
Isn't
Phi is,
phi is, so
Right.
if phi
But
of g
thi-
is pi g. Oh, well, I guess because you have different inputs.
right, so
it's
what I'm
a
asking
set
is,
of-
why does this pi g itself, why is it a bijection?
Okay, so each one would be a bijection, but then
So suppose. This means that G acting on A is equal to G acting on A prime, right? Now act on the left by G inverse. And this is the same thing as G inverse G acting on A equals G inverse G acting on A prime. And this implies that A equals A prime. So this, of course, is the identity, and that's true. So 1-to-1. Pi G is 1-to-1. I will see if you can prove that it is onto as well. It's not too difficult to do. Okay, any questions so far? Let me point out. Note. Look at A. This is GH acting on A. Which is G acting on H acting on A. That's root binding. And this is pi G pi H A. And so pi G H pi G pi A. So that is the action of GH is the composition of these actions here. So in particular, what that means is that P of GH, which is P, which is pi GH. This is pi G pi H, which is P of G P. So P G itself is a homomorphism. So given this action, this crazy thing that I came up with is actually a homomorphism. I'm gonna leave this, I've written it up in notes, but check that if you start, well, actually, you know what, I'll do it. Suppose we have an action. Our action gives rise to the homomorphism B from G to SA given by P of G. Right, that's what we've just done. Now, what if we take this homomorphism here and build an action from it? The action induced by B is G acts on A, well, star. Maybe it's a different action. G star A is B of G A. Right, that was our rule. And this is G right, of A. And what was pi G of A? It was G acting. So we recovered original action. So if you take the correspondence where you start the action, you get the homomorphism, and then you see the action from that, you get back to where you started. I will leave it as an exercise that when you start with a homomorphism, you get the action and then get the homomorphism back, you get back to where you started as well, and that is our bijective correspondence. So this is a cool big theorem because it says that, hey, any action is essentially action on A is essentially a homomorphism from G into SA and vice versa. Any questions on that? Yes.
So for the second part, P of G, phi from G to SA is phi of G, which is, so you plug in this element of G and then you get a bijective function. Pi
Yeah,
of
that's
G.
right.
Okay.
Yeah, so phi of G is actually this bijective function that goes, yeah, so phi, let me make sure I've got my notation. Phi is the homomorphism where your input is G and your output is a bijective function from A to A. Yes.
Quick questions. One, phi equals A. Is that phi should be at the top?
It means terrible, terrible. Empty set. Right. The
Oh.
things after this mean the homomorphism. I'm sorry about that. I should have framed that too. Right here it means the empty set. After that, it just means some homomorphism.
Wait, so A is empty or A is not empty?
Strike two. Not it.
Okay.
I'm not like there's about the empty set.
Okay, like at a very high level, go over like your approach to the proof, like what your if and thens were, because I followed the proof, I wasn't sure where we were starting, where we were trying to go.
Okay, so what we're doing is we're trying to show that if we start with an action, okay, well, actually, we start with a homomorphism. In the first part of the proof, I was given from on high a homomorphism that goes from G into SA.
Okay.
And I use that to get an action.
Okay.
So homomorphism gives me action.
Okay.
The second part, action gives me homomorphism.
Okay.
And then the last part that I was just doing here is
Okay.
when I start with an action and I get the corresponding homomorphism, and then I get the action back from that, it's the same action I started with.
Okay.
And the part I left out is start with a homomorphism, get the action, go back to the homomorphism, you should get the homomorphism to start
Okay.
with. Does that make more sense?
Yeah, I'll look over it. That's good. I got you.
Okay.
Thank you.
So there is like an F from the G acting on A to the set of homomorphisms from G to SA.
Yes, there is a function, and we described what it was by this process here. That starts with the actions and gives you a homomorphism. And there is another function G that starts with a homomorphism and gives you an action. And those two, when you compose them, they're the identity in both directions. Okay. Figure out. here. Given an action of a group on a set, then, one, the kernel of the action is the set of G and G that leaves everything alone. So the kernel of the action is everything in G that leaves everything alone. Alright, not just one.
Stabilizer?
No, a stabilizer is something that's specific to an element,
Well,
right? This is sort of the intersection of all stable elements,
just if it all stabilizers.
right?
You think that exam's not made on that?
Right, so
It's
for all
not
A
very
and
likely.
A, the stabilized with A. So this is. And get the notation G sub A, set of G and G, such that G A, so notice that this is specific to the element A and not a universal here. Three, if kernel of the action is trivial, that is the affinity, we say the action is faithful. Okay, any questions?
Like, that's G, the stabilizer is G today, and then what is?
I don't really have a notation for that. I just call it the kernel of the action. But we're gonna see, actually, we're gonna see it as an intersection of subgroups. Yes,
Why is this a theorem, not a definition? Just, doesn't it seem like there are three definitions there?
it does seem like that, doesn't it? Make a, let's copy it here. Yeah, I started, yeah, so. That. And I didn't make any statements that need proving, so. Definition again, 514. If G is a group, group and A is set in non-empty. A homomorphism from G into SA is called. So this is exactly the kind of thing that we saw coming up in that big theorem 512, whatever it is, a homomorphism from group into a set of bijections on set A is called a permutation. So it's just a homomorphism. So a permutation representation is, you might think of this as a way to write G as a bunch of permutations, as an element, or, contained in some symmetric group, perhaps. And definition 5.5. Let G act on A. So suppose you have G acting on some non-empty set, one, if A is an element of the set, so it's just something, then the orbit of A, I think this is a good terminology, kind of makes sense. It's just a set of everything that A can go to. So what you do is you take your element A, whatever it is, and you act on it by every element of the group and just see where it goes. That's where it orbits, right? As it flashes through the set A. What is one thing that for sure will always be in the orbit of A?
Oh, A itself, because the identity elements.
Correct. The identity is in G, so A is always in its own orbit for sure. Two, we say G is transient on A if there is deep orbit. And let me put that another way. That means that when you look at the orbit of A, it goes through every single element of A. Everything's covered. So that is, given any two elements in the set A, you can find an element of the group that acts on A and takes it to D. Okay, any questions? Okay, so here, yes,
Well, so unique orbit meaning. The orbit is. What does that make it a unique orbit?
because if you pick any element of that set, I don't care what you pick, and then you start acting on it by elements of G, it will cycle through the entire set. Right, and so there's only one, everything is in the same orbit. Everything in the set's
Not
not, same.
that the element has a unique orbit, it's only one orbit for.
There's only one orbit.
Okay.
Right.
Thank you.
Theorem, let G be a group acting on the set A. Suppose G acts on the non-empty set A. We're going to declare an equivalence relation. A is equivalent to B if and only if A is equivalent to B if and only if there exists G and G such that G such that A and B are connected. That is, we declare they're equivalent if and only if they're in the same orbit. So this is a relation. Tilde is equivalence relation. On set A, and for each A and A, what is more, for all A and A, the number of elements in the equivalence class of A is And by the number of elements, I'm using that class list, this could even be an infinite, this could even be infinite. The number of elements in the equivalence class today, under tilde, is the index of the stabilizer of A in G. So the length of the orbit of A is the index of the stabilizer. This is a big theorem that will help us count. The length of the orbit of A under this action is just the index of whatever the stabilizer is. So let's establish this theorem here. Right. I guess the first thing I need to do is kind of convince us all that this is in fact an equivalence relation, right? Okay. Well, notice. Okay, so it's reflexive, right? And we also need reflexive and transitive. Two. Suppose A is equal to B. This implies that B. What do you think I'm gonna do next here? I've got to get B is equal to A, right? So tackle this with G inverse. So G inverse is also an element, so there you go. And A is equivalent to B and B is equivalent to C. This means that G A is B and G prime, whatever choice, H B equals C, where A B C is in A and G H G. Well, so what do I need? I need A to be equal to C. But notice H G A is H acting on the B, which equals C, and of course, this is H G on A, so translates. So, okay, you've got that lick. It's an equivalence relation. Now I need to do this other business here. The claim is for every A and A, the number of elements in the orbit is equal to the index. Well, now the equivalence class of A is the set of G acting on A, such that G is equal. The equivalence class of A is precisely the orbit of A, right? It's everything that's in A's orbit. So what I'm going to do here, let L set of left cosets of GA in G. So this is going to be the set of see this. Set G A. So L is going to be the set of left cosets, and I am going to define a function f, the set of left cosets into the equivalence class of A. And I'm going to do it this way. little f of G of A is G A. Let's note that if, let's note first that F is onto the equivalence class of A. Because anything in the equivalence class of A takes on this form, so it's clear what the coset that goes to that is, it's G. And so let's see why this is 1-to-1. Suppose F here equals H here. This implies that G acting on A equals H acting on A. And this means that H inverse G acting on A equals A. So where is H inverse G? It leaves A alone, so it's been stabilized. So, that means these two cosets are the same. So F is 1-to-1. And this gives us what we want, because this means the cardinality of L is the cardinality of the equivalence class of A, because this function is a bijection. So there. And that's it. Any questions? What's that?
How is it 1-to-1? You just assign the level.
So
Or I meant onto.
what, oh, how's it onto? Okay, so an arbitrary element of this is of this form. Right? And how am I gonna get to G? Just take this coset here.
Oh, okay.
Right, and so. Others. Okay, well, don't forget that, okay.